Oh, well, you can't win them all, can you? Now, what am I, a professor of electrical engineering, doing potting at ping-pong balls? It's not just that I think science ought to be fun. I do have a serious purpose in mind. And it isn't the shooting part that interests me. It's how these balls stay suspended on the water jets that really fascinates me. You could ask, of course, what an electrical engineer is doing dabbling in hydraulics anyway. And the answer is that I can see what is actually going on. You see, my own subjects are electricity and magnetism, and both of these are invisible. I'm trying to make a model of what might actually go on in a magnetic circuit, which behaves in exactly the same way as this water circuit. In other words, I'm trying to make the invisible visible. Now, the thing about analogues is that you need to know just how far they can be useful and just when you have to shoot them down. I want you to see this as a circuit. See, when the water has hit the ball, it falls back into the trough and then is returned through pipes back to the pump. Now, of course, we can make the whole thing neater by enclosing it all in pipes, like this. In this circuit, the driving member is here, the pump. This is a valve or switch. When I open the valve, you will see a plunger rise in this tube here. This is recording the rate of flow of the water. Here is a manometer recording the pressure difference between 2 points in the circuit. The manometer is connected in here and in here so that it measures the pressure in this piece of pipe there. And this water circuit has been designed to be the analog of an electric circuit, like this. Instead of a pump, there is a battery. Instead of a valve, a switch. And instead of a water flow meter, an electric flow meter or ammeter. This voltmeter can be connected either to that point or to this point. And by subtracting the two readings, we can measure the electrical pressure drop along this part of the coil. So I'm using something that I know about to help me explain something I know less about. Now, the trouble with analogues is that none of them are ever completely true. So let's see how far we can take this water electric analog before it breaks down. First of all, if I replaced this rigid pipe with a flexible hose, then when I turn the pressure on, it would blow out like a garden hose pipe does and try and make itself into a circle. Now, will the same thing happen with the electric circuit? Suppose I were to replace this coil with a more flexible one. What do you think would happen? I'm going to use a loop of aluminium foil. Ordinary kitchen foil will do, but the thinner the better. When I switch on the current, you see it does bow out like the water pipe. I mustn't leave the current on for too long each time, otherwise I shall burn out the tape. It takes about 20 amps to do this. Now I'm going to try something different. I'm going to hold a bar magnet alongside, and this time when I switch on, something very different occurs. And of course there's no equivalent of this in the water circuit unless I can get hold of a water diviner and his hazel twig. But then, you know, you always get into difficulties when you try to explain the behavior of permanent magnets. Let me show you what I mean. I'm going to use two bar magnets, and first of all, I place them with like poles opposite. So, of course, they repel each other. If I put a bit of steel now on the pole of that magnet, I don't change the polarity of it by just doing that. If that was a north pole before, then the outside of the steel will still be a north pole, and so it should still repel the other magnet, shouldn't it? Surprise, surprise. Now, in that condition, both magnets are pulling on the steel outwards. They're trying to split it in half. Let's give them the opportunity to do that by making it a double piece of steel. Now, when I release my fingers, will they in fact succeed in pulling it in half? They do. Now, here's a situation, isn't it? In that condition, they just don't want to know each other. But with only a single piece of steel, both magnets are quite happy to attach themselves to it. I told you permanent magnets were going to be difficult, but believe me, there's worse to follow. Suppose I take an unmagnetized steel ball and an unmagnetized bit of steel. I'm going to put the steel ball on the magnet pole. As I approach it and touch it with the unmagnetized bit, I can always succeed in bringing the ball away with the unmagnetized piece. If I put a bit of cardboard in between magnet and ball to begin with, you can actually see the ball jump away from the magnet. Now I'm going to suggest that an explanation of these phenomena using the pole concept would be very difficult indeed. So what analogue can I find to help me with an explanation? I'm going to use an analogue of a magnetic circuit. This is an iron ring, and it carries two coils, a large primary coil and a smaller secondary coil connected to an ammeter. When I switch a current from a battery into the primary coil, there will be a momentary current in the secondary. I'm going to remove the meter and replace it across the secondary with a small lamp. If now I can change the current in this coil continuously, which I can do by feeding it with alternating current, then I can light the lamp continuously. It seems as if the iron ring is acting as a sort of transmitter of something or other between this coil and that one. And we call this something a magnetic flux. Now let's see what will happen if we take the iron ring away entirely. Now with the secondary coil in the same position as before, I switch on the AC as before, and now the lamp does not light. Now this magnetic circuit is not quite the same as the electric circuit. Let's see what happens if I put the iron back, but keep a gap in the circuit. Now it looks as if we've broken the circuit completely. Nevertheless, when I put on the coil and switch on the AC, we light the lamp, even though it's not as bright as it was before. So it seems that our magnetic flux can jump this gap, and that air itself is a conductor of magnetism, even though a weak one. Even if we take the iron away entirely, there would still be an effect, even though it wouldn't be enough to light the lamp. Now let's apply these findings to our permanent magnet systems, looking at the permanent magnet in a quite different way. On this board, I've drawn out the lines of force as they would appear from a bar magnet there. But I've drawn them out in electric wire, because instead of a source of magnetomotive force, I'm going to use a battery, which is a source of electromotive force. I'm going to measure the current flow in these lines on this meter. When I switch on the battery, we're now measuring the current in all the wires together. Now remember that air is a bad conductor of magnetism, so these are high resistance wires. In this context, steel would be a good conductor, so it's represented by this piece of copper. When I put the copper down on the wires, the current increases because I'm short-circuiting some of the high resistance parts. And as I slide it round towards the pole, I'm covering more and more wires, so the current continues to increase. The law of nature is such that it will always try to reduce the reluctance of the external circuit. And this is the rule we shall now use in place of the rule of magnetic poles, and we can use it to explain all the phenomena of magnets which we saw earlier. Now you don't have to understand something which you can see in order to use it as an analogue. Suppose, for example, that I wanted to understand the behavior of molecules in a gas which I can't see, using something which I can see. Now, although we don't understand in the strict sense of the word magnetism, the behavior of magnets is familiar to me. So I'm going to use lots of small magnets to represent the gas molecules. Each of these magnets has been cut from a sheet of rubber which has been impregnated with barium ferrite and then magnetized. They're in a transparent box on top of a row of electromagnets. I'm going to put a transparent lid on top of the magnets and then switch on alternating current. The movement is exactly the same as the movement of gas molecules, entirely random. The lid lifts because of the impact of individual particles on it, and this is what we call the pressure of a gas. Now suppose that I move in a plunger from this end and compress the gas into half its original volume. Keeping the voltage the same, the lid now rises twice as high, and this is what we call Boyle's law. I can change the temperature of the gas by changing the voltage that I supply to the electromagnets. Let's try this. I can raise the temperature like this, or lower it like this. Here's another demonstration you can do with this apparatus. If I take the lid off entirely, then I can show either evaporation from the surface of a liquid or the diffusion of gases. Individual particles will have fortunate collisions with their fellow particles and be ejected entirely. When smoke is introduced into a gas and then examined under a microscope, bright flecks of light are seen dancing about. This is known as Brownian motion. It's used as evidence of molecular activity, even though it's known that the molecules themselves are not being seen. The smoke particles are being buffeted about by the molecules. Now, I can put smoke into my gas in the form of paper balls, which will not be affected by the magnetic field. Put a lid on and switch on. And there is the Brownian motion represented in the analog. Now I'm going to connect up the motor in a different way so that the electromagnets produce their maximum flux at different times, and so that the whole effect shall be that of a traveling wave of magnetic field. Now watch what happens to the particles. We are effectively pumping the gas to one end of the box. Now, can we do this in real life? Can we pump gases without a piston? I suppose what I'm asking is, can we operate on individual gas molecules with a moving magnetic field? And the answer is that we can, if we can strip an electron off each molecule. In this state, the gas is said to be ionized. Now, this whole process of gas pumping has the wonderful name magnetohydrodynamics. I'm afraid I can't show you MHD, as it's shortened to, very simply, but I can demonstrate that we can pump fluids, at least by pumping mercury rather than a gas. This trough has a piece of steel fixed into it to improve the magnetic circuit of this motor. When I pour mercury into the trough, it's going to flow underneath the piece of steel and be pumped along the bottom, up this end, and flow back over the top. Now, when I switch on the magnetic field, you can see the mercury making a small fountain at this end. It isn't easy to see mercury flowing, but you can float a coin on the river, and I hope that this convinces you that we can pump fluids electromagnetically. Now, this same magnetic field is much more potent if it operates on an aluminium sheet instead of on the mercury. The reason for this is that aluminium is about 40 times more conducting than mercury. Of course, I could make it more potent still if I could put some steel behind the aluminium to improve the magnetic circuit. But instead of this, I'm going to change the shape of the motor. Can you imagine that the two sides were bent upwards and the whole thing rolled up into a tube? Having imagined that to be done, let's make a machine that looks like that. We should find that the windings are very simple, being only a row of coils like this. The moving part is a steel rod with a copper sleeve around it. We put it in the end of the tube and fire. Well, that wasn't a bad shot, was it? This electromagnetic gun seems to have taken us right back to the start with our rifle. It looks as if we can make an electromagnetic model of nearly anything. We've certainly managed to reproduce the gun, but can we also reproduce the target? Can I float a ball on a magnetic field in the same way that I floated the ball on the water jet? Well, here is a ball. It's made of aluminium, and this is going to act as our jet, a single coil which is going to carry alternating current. I switch it on. The ball is certainly trying its best to float. But you see what's happening? It's like trying to balance a pencil on its point. What we need is some inward force which is going to make it drift back every time it tries to get off center. There seems to be no equivalent of the surface tension we had with the water jet. Now inside this coil there is a second coil, and I'm going to feed this with alternating current of a different phase so that I can produce an inward traveling magnetic field which I can detect with our rotatable cylinder. Notice that the bottom of the cylinder is always moving inwards. And now when I replace the ball, it does. Now it's one thing to float a ball as big as this, but what sort of apparatus should we need to float a ball this size? It's a different world, you know, from the world of ping pong balls. Barry, if you just come and take the ball back slightly, we can see what we've actually got. Now this is a sort of exaggerated version of the small ball coil. The inner coil is set down deeper in relation to the outer. First of all, we're going to send current through the outer coil only, as we did before. Would you like to come on the switch, please, Jim? Now, Barry, you and I have got to catch it, otherwise it might damage itself by falling back. Ready, Jim? 3, 2, 1, on. Right, lower it, Barry. Let's try and balance it. No, off, Jim. Again, it isn't stable with a single coil. Could you connect the other coil, please, Jim? Now, would you take the ball away, Barry, please? Now, I'm going to check the phase sequence of the two coils using a rotatable cylinder, which I've used before. What I want to happen is the magnetic field to go down the outside of the cylinder and so rotate it in that direction. So I want to see the cylinder spinning that way. Switch on, Jim. Switch off, Jim. That is the correct direction. Now, Barry, if you could have the ball, please. Now, this time, it shouldn't drift off. This time, you should fairly be able to see the magnetic flux spraying off the sides like you did the water from the ping pong ball. It might even spin for us. You can never tell just what this ball's going to do. If it spins, then we shall indeed have come full circle in the circle of magnetism. Ready, Jim? 3, 2, 1, on.